Hi. So I'm going to cheat. I'm actually not alone, so nobody needs to wonder what's going on here. So I also run out of breath a lot lately, so just bear with me. I'm going to talk a little bit about keeping things simple. So one thing that happens when you start venturing into machine learning land is you get seduced really easily by all the funky things that you can do. And this rears its head a lot in hiring especially. So whenever I have interns applying for a position on our team, I'll ask a question, how would you solve this? And I build a convolutional neural network that's such and such and such, when really all you need is a linear regression. So I'm not going to just talk about that, but I'm going to talk about the kinds of things that you can have sort of top of mind, and the heuristics that you can build and the frameworks that you can work within to ensure that you're not really deploying overly computationally intensive solutions that may end up being a beast to both maintain and support and explain as you go forward. So first of all, I want to tell you a little bit about where I work, which is at iRobot. So iRobot has been on the Boston scene for about 27 years. It's now truly a global company, and there's a lot of people who know what they're talking about. I run data science there. Data science is a new discipline at iRobot. We've been around for about a year. Actually, a year, 2 weeks ago. So we've been helping them sort of manage they have brilliant roboticists and algorithmists, but my mandate is really to look at fleet-wide behavior. And so that's where those algorithms come in. Obviously, the robots have their own algorithms, navigation, location, mapping, but that's not what I'm going to talk about. I'm going to talk about sort of fleet-wide behavior. As I mentioned, iRobot now is a global corporation. We've closed 2 massive acquisitions last year. We now have presence pretty much in every time zone. So if you know anybody who wants to work at iRobot, let me know. The odds are we have an office where they can work and help make a difference. Also, as I mentioned, we've been around for a really long time, and we sort of know what we're talking about in terms of robotics at this point. We've done things across the gamut. So the company started trying to get robots into space, which I think it's just freaking awesome. And through our history, there's been an evolution where it's always been about impacting people, so saving lives in a military context, saving lives in hospitals and in sort of a healthcare context with telepresence. But for lately, I think as of 2016, early 2016, we've really become a consumer-focused robotics company, really the premier consumer-focused robotics company. And we have millions of robots deployed around the world. And really lucky for me, because that's my bread and butter, a lot of that fleet now is connected. So a lot of those robots are phoning home, and I get to see what they're dreaming about. We have huge expertise across all sorts of technology realms. Mapping and navigation, as I mentioned, some of the best in the business are working, making sure that our robots know where they are and know where they're going. We have some of the best people in the business in terms of human-robot interaction and human-computer interaction, and making sure that the whole experience is designed from the ground up. Physical solutions and the hardware that is involved in deploying the fleet, as well as the smart home and developing a whole ecosystem that within which the robots can operate. So let's get into the meat. I'm going to talk about 3 things as we think about deploying machine learning algorithms into production environments. I'm going to talk about purposefulness, complexity, and resilience. And then hopefully we'll have some time for questions. So in terms of purposefulness, the way to think about this is, what would you rather have? Would you rather have 100 sensors that are off by 40% or 500 sensors that are off by 10%? Would you rather have small fraction of your fleet that's catastrophically off, and do you have robustness within your purpose to withstand that kind of small fraction of catastrophic behavior? Or would you rather have the vast majority of the fleet sort of vaguely right instead of precisely wrong? And those kinds of constraints that you live within are going to drive the kind of choices that you make in the selection of the algorithms that you employ. So the things to think about are, as you're thinking about how you're going to employ them, there are system constraints and there are solution constraints. So in terms of system constraints, things that you may not have control over. So for instance, in my team, we are consumers of a lot of the architecture that's put in place. All of that data is transmitting, and all of that data has to percolate the system and ensure that customers get what they want when they open their app, things function correctly, and when they see the information about their robot and the experience that they've been having with their robot, that it matches the experience that we are showing them that they are having. So those things have to be have to work in tandem, and a lot of that I don't have control over. I don't get to choose all of the different steps that data goes through by the time it hits me, and I run an analysis, I employ an algorithm, and then I serve an answer that then gets plugged back into that architecture and served to the different consumers of that information. In terms of explainability, I've worked in several different industries, not just in robotics. As I mentioned, data science at iRobot is very young, but I've worked in the energy field. I've worked in medical, clinical, med devices, agriculture. So regulation is something that sometimes you can't have any control over, and you have to have interpretability, explainability, things that you have to explain why it is that your algorithm, that your system behaves the way that it does. And so that may preclude certain choices, that may obviate certain choices. Also team structure, sometimes you have the luxury of having data engineers, data architects, API architects, people who are going to help you orchestrate the whole system, and they have expertise, depth of expertise. And sometimes you're a startup and you're relying on 2 or 3 unicorns who sort of know everything and don't know anything, just by virtue of the fact that the brain is finite. So, and sometimes budget, actually always budget. Nobody controls budget. In terms of solution is really the levers that you do have control over. So accuracy and speed trade-offs are usually something that you're dealing with, so much faster algorithms are usually going to be much more loose in terms of their precision. Also buildability over time, so do you want to start small and be able to increment with different pieces, or do you want to just throw spaghetti at the wall with the most complicated thing you can think of, and maybe it works, maybe it doesn't. So those are the kinds of things that you may have control over, and you wanna always start small. But sometimes the thing that you have no control over is deadline. Maybe this has never happened to me. Thankfully, but sometimes your CEO goes on the Wall Street Journal and says that something is going to be done. So, for instance, recently, a CEO of an autonomous driving company said that they would have full autonomy, level 2 autonomy in 6 months. And that deadline came and passed because, these things are hard. So in terms of the trade-offs that you're making, one thing to keep in mind is that these things are not linearly related. So whether we're talking about time, whether we're talking about team, whether we're talking about incremental buildability, these things are usually shaped such that there's an inflection point somewhere, and that inflection point is really difficult to predict, but it'll always bite you in the behind. So, and the other thing to keep in mind is that you're never going to get to 100%. So don't promise your CEO that you're going to get them 100% certainty, because that would likely require you to take their entire R&D budget for the next 5 years. It's not worthwhile, and it's usually something that with a little bit of a difficult conversation up front, you can have them be advocates for your position rather than adversaries. So how do you get all of these things to play together, right? How do you actually deploy these things? Well, sometimes it's really hard to explain what it is that you're trying to do, especially when you have lots of teams involved and not everybody has a math background, a statistical background, or a data science background. You have some really brilliant people who are software developers or data architects. And so the thing that you need to think about is how to articulate these requirements, and the looks good way of articulating is something that I have found translates really well, and quantitatively defining that looks good requirement is that translational step that gets you to where you want to go. So what does it mean to look good? Everybody knows, right? The famous saying in the Supreme Court, and I always blank on the actual justice who said this. It wasn't Thurgood. I'm sorry. You guys are at Google. Google it. But he said, in terms of pornography, it's hard to explain, but you know when you see it. For our intents and purposes, it's hard to explain, but you gotta explain, because that's how you actually code. That's how you write software, is you define things. So defining what looks good, you can do that in terms of edges that don't match up. You can talk about values that are atypical, slopes that are atypical. So you can look at the criteria that make up the curves that you're trying to predict or extend or extrapolate, and think about all of the pieces that make up that curve, and then talk about the atypical nature of those curves. And here you can see this is a particular curve that we were trying to do VEE with, which is verification, editing, and estimation. So you verify that things are where they are. You edit the things that are misreadings from the sensors, and then you estimate over gaps or pieces that have been edited out. So the blue is the stuff that the algorithm did. The red is the stuff that the sensor read. And you can see, just eyeball, you guys don't know what field this is in, but you know that there's something really wrong with that increasing slope in blue, right? So quantitatively articulating what that means, why your gut tells you that that's wrong, and just writing that down in the documentation gets you very far. And here's another way to think about it. So as we were trying to interpolate those curves, these types of curves, and I don't need to tell you what they are because the whole point is developing this gut heuristic. We tried several different iterations, and what we were looking at here is how long does it take to compute each of these, how accurate are they, and how accurate are they for our intents and purposes. So does each individual microsecond need to be accurate, or does the overall value of the curve need to be accurate over a certain period of time for regulatory purposes, for settlement purposes, for agreement purposes? And so here you can see all sorts of different approaches that we took. Some are actually mighty complicated. Some are really simple. Some are just find the average point at the gap and just draw a line in between. And so because I like to think that we are not in the business of making judgment calls. We are in the business of solving problems. Our product managers are in the business of making judgment calls. So we provided them sort of a menu of options, and they got, because they have a lot of domain expertise, they understand the customer, they understand the situation, they understand the objective much better than we could. We try, we're good at it, we're great at it, if I could say so myself, but we have a day job and they have a day job, and their day job is to look at this and pick the right one. So not trying to solve, but trying to provide solutions that somebody can pick from, also a really good approach. And as we talk about machine learning, we're often talking about cost functions or objective functions. different tribes have different names for this. But when you're thinking about designing your objective function of your algorithm, you can also think about designing the objective function for your project, almost thinking about it as a meta-objective function where you're taking lots of things into account. So for a particular algorithm, you may do gradient descent, and that gives you the solution that approaches the objective that you set out for a particular algorithm. But if you have the objective of your project to be, I want the solution that best solves my product manager's problem, there are all sorts of different criteria that you can include in that meta objective function. So things like making sure that when your result is getting worse, the cost metric is matching that. So sometimes, especially when you're dealing with really, really, really smart people, they can get lost in the academic exercise and they can forget that what the algorithm is doing is somehow opposed to what the objective of the project is doing, and you end up with a really phenomenal algorithm that you can write papers about that you then shelve because you can't actually put into production because it doesn't do the thing that you set out to do, but it works great. You can also have meta objective functions that make sure that underestimates and overestimates are taken into account, following the same rationale. And you want to make sure that as you're imputing values and you're taking care of outliers, that you don't have 2 or 3 data points that are hijacking the whole calculation. So again, that's the kind of thing that gets sublimated when you're just thinking about it in terms of the specific mathematical objective function. You sort of have to step back and look and make sure that this isn't taking place. But as you think about all of these different objectives that you're trying to solve for, it's important to remember that there's only one objective. And the objective, depending on what your objective is, if you're in government, if you're in the civic arena, if you're in a corporation, if you're in a startup, you have to follow that objective, and that objective isn't to be right. For instance, in corporate America, usually that objective is to make money. So you want to make sure that you are thinking about it in terms of what is the team goal, what is the overarching goal, rather than thinking that the objective is to have this linear regression have a really, really small R squared. So back to that objective function thinking, the things that you want to think about are things that are specific to your model, and then things that are specific to your business. So in terms of the model, the ever-present bias variance trade-off, you have computational complexity that you have to take into account. You have to think about cross-validation, and do you have enough data points to segregate and test on? You have things like design optimization that you have to think about. But you also, and this is where I put my management hat on, you have to think about costs of computation and costs of the architecture, and how many queries are you going to be running, and how many exfiltration of data, and how much transfer of data is your model going to require in order to run. As I mentioned, model explainability, sometimes making a trade-off decision where the model is actually much simpler, but you can get buy-in, and you can sometimes incrementally get your team to a point where you can actually deploy a really sophisticated solution. And sometimes it's not just your team, sometimes it's your customer, right? You can take your customer on that journey where they're building their own heuristics as they're interacting with your product, such that they start expecting better results, that if you were to start a brand new product with a really sophisticated solution that is very hard to explain, you may get a lot of pushback. Data availability is another one that is huge, so you can't always depend on the data being available. There are latency issues, there's intermittent connectivity, there are customers who change their Wi-Fi password and then forget that they changed their Wi-Fi password, and then their robot's been running for months without ever sending you any information back. So those are the things that you have to sort of think about in terms of the business, and then have that objective function that sometimes forces you to have really difficult conversations with your team, because they really want to have different solution than the one that you're proposing. And this is a really good way of having that conversation and explaining that it isn't just because I said so. And this is something that I'm going to have to remember, because with him, I'm going to be able to say, because I said so, because I'm your mother. With your team, you can't do that. So this is all to say, as you're thinking about the purpose of your machine learning implementation, and as you're trying to make sure that you're keeping things as simple as possible but no simpler, the thing to remember is that your intuition isn't sufficient, because your intuition is only as accurate as your cumulative experience. And so really quantitatively describing and defining and articulating all of those steps that you've navigated through in your trade-offs really helps you maintain credibility with your team, especially as you move towards the more strategic decision-making aspect of the team participation, and you move a little bit more away from the technical hands-on keyboard linear algebra portion of the experience. So that's purposefulness. The second thing that I'm going to talk about is complexity. So the thing about machine learning is that everybody is familiar with garbage in, garbage out, but what happens with machine learning is that you're doing garbage in, garbage out at scale. And these things get unwieldy and out of control really, really quickly. And so you want to be aware of what's happening from the get-go, because what you don't want to do is look back 3 weeks later and figure out that, holy moly, some things somewhere really went out of whack. And this one is really key. So as you're talking to people across the organization, it's really easy to default to a feeling that, oh, these people just don't care. Nobody gets me. Nobody understands the power of data and the importance of data. And that's not what it is, right? They care about different things because they're incented to care about different things, because they're trained to care about different things, because they've experienced different things, right? As we think about that awful situation that just happened in Hawaii with the ballistic missile alert going on, that guy is never going to make that mistake again, right? That guy cares from now on. Right? That's how you build all of these heuristics, is you make really, really big mistakes, and hopefully they're not catastrophic that they torpedo your career, but you're now trained to be aware about these things. And if you've worked with data your entire career, like me, I've been working with data for about 15 years now. I've made a ton of mistakes. I care. Folks across the organization may not be prepared to care, but it's not that they don't care. It's just that they've not been through these situations. And so it's your job, it's incumbent upon you as a data professional, not just to give the answer, but to train those around you in the business of caring. So how do we make them care? We make them care by telling them where things can go wrong, and sharing the mistakes that we've that we've experienced, so that they can feel the pain without going through the pain. And so I don't know how many models you guys have deployed into production, but once you have lots and lots of moving parts, suddenly you have a legacy model that nobody knows how to fix and nobody touches, and it has so many moving parts, and each corner of that model was built by a different person who is now on their third job since they've left that company, and you just don't touch it, right? That's bad. So you want to make sure that you have as few moving parts as possible, and that everybody is trained on all of those moving parts. So what you don't want is a hospital with tons of specialists. You want specialists because that's a good thing, but you want to make sure that your pulmonologist understands how the GI tract works. Not because you want the pulmonologist doing GI surgery, but because that pulmonologist might get a new job. And you want somebody to be able to support that that piece of software in the analogy, without having that be relegated to the corner of, this is legacy code and we just don't touch it anymore. Things like the number of seconds to complete. Sometimes things run out of control, and then you just have to dedicate tons of compute power to a particular piece of the whole entire puzzle. Again, because that piece nobody knows how to fix, and that piece takes forever to run, and so you just throw compute instances at that part, and every other part of the system suffers. Type safety. So who are my Java people? Where are my Java people? Yeah, you know what I'm talking about. Every other language, when they're doing their part of the whole complex system, and then they send you a packet with their information, and it's not type safe, and then your piece of the puzzle explodes, and suddenly it's your fault and not the fault of the person who handed you the baton, because their code was not type safe, and things blow up, and it's really hard to figure that out. If you've suffered through that, you know what I'm talking about. And also, again, cost. Sometimes you end up having to lay off team members because the cost of the actual machinery is too much, that money has to come from somewhere. So if that's a pain that you've had to feel, you know that watching out for the costs of running, but also the costs of hiring. So if you have a system that is built on 18 different languages, including assembly, that's going to be really hard to hire for, and that's going to be really expensive to hire for, which means it's going to be really difficult to maintain and to store, because then you have to have all sorts of different types of storage that can handle multiple definitions. So, going back to the metaphor of constraints and control, I had talked about things that you can control within your solution and things that you cannot control within the system. So they're always, right, you can always plot things on a 2x2. So if you have something on the top left quadrant where you have very low system complexity but very high solution complexity, that's where your rebels come. That's where your really dedicated, super smart, brilliant researchers want to play. They want to play because they want to have all of the really funky new approaches to things, and nobody outside sort of in the system realm telling them what they can and cannot do. This is where they have free reign. They can just rule the jungle. But if you have people, if you have a system that has very low complexity, but your solution also has low complexity, that's usually where trouble brews. That's where you have people who solemnly swear that they're up to no good. So that's where things can go wrong on the other side. So this is where linear regression and logistic regression should reign. But because there's very little constraints all around, this is where you get very junior folks who throw a CNN onto a problem for absolutely no reason. So that's where you want to watch out. If you have high system complexity but low solution complexity, that's where the magic happens. That's where, if you're really paying attention and you're really aware of what the system constraints are, that's where you can really paint beautiful art, because that constraint enables all sorts of creativity that you can work within, because you have all the freedom in the world in terms of the solution. If you have a complexity of solution and complexity of the system, that's where you need surgeons. That's where you need precision, and that's where you need stamina, and that's where you need folks who understand that it's going to be a really difficult situation, and they're in for the long haul, and they're going to have to be alert for 18 hours performing that very difficult procedure. So what you want to do is you want to stay to the left, right? You want to make sure that you have low constraints of the system. So how do you do that? First of all, remember that there's lots of breadth. Try lots of shallow solutions. Engender serendipity. Make sure that you create space so that those creative solutions can come to you. In terms of the evaluation criteria, make sure that you're including simplicity as one of the evaluation criteria as you are looking at all of the solutions. So as I mentioned way early in the presentation, one of the solutions that we had was literally, we have a gap, figure out the average between the 2 points and just draw a line, because it may be that that is perfect for the intent of the problem at hand. Also remember, what is good enough, right? Sometimes you don't need to draw all of the surface texture. Sometimes just a splot of paint is sufficient for what you're working on. And don't forget to get clever, right? Sometimes you don't need to prove to your professor that that was the correct solution. Sometimes you don't have a committee adjudicating. You don't have to defend your thesis. Sometimes it just has to work. To close the complexity part of the conversation, I like to bring up Oliver Wendell Holmes. So this is one of my favorite quotes. He says, I wouldn't give a fig for simplicity on the near side of complexity, but I would give my right arm for simplicity on the far side of complexity. So as you think about, you have very simple solutions from somebody who hasn't really thought through the implications, and they're very shallow. And then you have very complex solutions that are very difficult to implement, and they're beautiful, but they're beautiful in this really complicated way. And then when you cross through that and you get to the far side of simplicity, is when you have elegant solutions, right? That's where elegance springs from. And that's what you're looking for. You're not looking for shallow simplicity. You're looking for deep simplicity. You're not looking to avoid complexity. You're looking to pierce through complexity. So lastly, I'm going to talk about resilience. How am I doing on time? I'm going to breeze through this one so you guys can ask questions. So as I've been talking about, you have solution reliability and system reliability. So let's start with solution reliability. Here's the thing about reliability. You can have a little pond in your backyard or your grandpa's backyard, and you want to put a bridge over it. That bridge can be just a bunch of wood stacked on top of each other, and everybody's going to climb over that, and nobody's going to die. But if you do the same thing, connecting Manhattan to Brooklyn, that same mentality is not going to work. So as you're thinking about how do you build the reliability of your solution, these are the kinds of things that you have to think about. How many times is this function going to get called? How many times is this architecture going to get traversed? How much data am I going to be pumping through these pipes? And you want to make sure that you stay as simple as possible, but no simpler. So one way to think about this is to employ golden data sets. So golden data sets can be a mixture of real case, but also synthetic data that you can envision sometimes hitting your system, but may not have hit your system yet. So you want to look at all the examples that you have seen that will be applying to your that will be going through your system, but you also want to think about all of the weird edge cases. And what you want to do is you want to use all of that, put it through your system, and see what the output is, and then match those things with your system reliability team, so that they know that when they translate your little pristine academic lab model and they push it to production, that what they pushed matches exactly what you want to match. And one way to do it even better is to have it employ a testing harness that adds error. So you want to chaos monkey the implementation of your model. So you want to have the algorithm get you want to have information flips, you want to have bit flips, you want to make sure that the system is robust to the kinds of things that happen in software, because these things happen. You want to make sure that if a server goes offline, you're not yielding bad information, you're yielding alerts. And those alerts, that bad information is labeled as bad rather than just passing right through without anyone being aware that something has gone wrong. So you want to do that all in the testing phase. In terms of the system, it's not that math is negligent. Math don't care. So if you put in something into production and it passes all the tests, that doesn't mean it's good. That means it passes all the tests. And there's some really bad math that can pass all the tests. And those are the really finicky ones to find. So the way to ensure that you are not that you're not going to get caught in that is to have a diverse team. To have people from different walks of life, with different backgrounds, who come from different programs, with different disciplines. So, for instance, everybody has blind spots, and you want to make sure that everybody's covering each other's blind spots. So, software engineers, in my personal experience, tend to have a bit of trouble with sampling. Deep learners have some trouble with truly rigorous statistics. PhDs have trouble with shipping things. Sorry. Statisticians tend to forget about unit tests because math just works, right? Visualization experts tend to be vulnerable to overfitting, and managers, we tend to be vulnerable to p-hacking. We are, I admit it. So this is what happens when you have dynasties, when you have teams that are built of just PhDs who came from the same university, who came from the same lab, who learned under the same experts. You end up having dynasties, and you end up having intellectual inbreeding. And the same thing that happened with genetic inbreeding with the royal dynasties of the 14th and 15th century Europe, the same thing is going to happen to your teams and to your solutions. And your solutions are going to be vulnerable to all sorts of genetic mutations, intellectual mutations. And the worst part of that is that you're not going to be aware that that's taking place. It's going to go right over your head. So just like we apply multiple objective decision analysis, which is a type of approach to solving these kinds of problems, you want to apply multiple objective decision analysis to your hiring. So you want to have folks who come from, who have different perspectives, who have different levels of seniority, right? It's not charity to have lots of interns. It's not charity to bring in junior folks. They bring in something that's magical, which is the luxury of ignorance. They don't know that they're asking dumb questions. And guess what? Most of the time, those questions end up not being dumb because they illustrate something that perhaps has been overlooked because we've forgotten to ask those questions over the years. You want different backgrounds. You want folks who have experienced different things. So I come into robotics from a background of energy trading and clinical trial planning and agricultural genetic trade integration. And all of those different experiences, sure, data is data and math is math, but what that allows me to do is to cross-pollinate and to bring really interesting backgrounds into problems and to solve them in different ways. I have somebody on my team who has a background in marine biology. And so as we're thinking about robot fleet behavior and robot cooperation, she's bringing her background in dolphin pod migration and observing how those ecosystems work and bringing those. This research exists. There's tons and tons of papers. We just didn't know to go look and read that kind of math because we were stuck in this kind of math. So anyway, this is just to remind you that this is from Deb Chakra. She's a professor here in Boston. Any sufficiently advanced negligence is indistinguishable from malice. So it doesn't matter if you don't intend to be malicious. If you're sufficiently negligent, that's what's going to come out. So